Hey everyone! In this video, we're diving deep into real-time machine learning inference and low-latency serving architecture.
90% of machine learning models never make it to production because of serving bottlenecks. At YouTube scale, that's millions of dollars in wasted training. Here's what trips up most ML engineers. They optimize for offline accuracy, but neglect real-time latency. By the end of this video, you'll know how to design a low-latency serving architecture that can handle millions of requests per second. We'll see why this matters when we discuss caching strategies. Before we dive into the architecture, let's define our metrics. Offline metrics like NDCG and AUC are important for model quality, but they don't tell the whole story. Online metrics like CTR, conversion rate, and engagement are what truly matter. We also need guardrail metrics like model freshness and prediction stability. Remember that 90% failure rate we mentioned? Stale models are a major contributor. Ultimately, we're trying to maximize business KPIs like revenue and user retention. A senior engineer would ask, what's the latency budget to achieve these KPIs? Now let's talk data. Our data sources include user activity logs, item metadata, and contextual information. We need a robust data pipeline to transform this raw data into features. Think of the feature store as a restaurant prep kitchen. Ingredients pre-chopped and ready so the chef, model, can work fast. We need both real-time and batch features. Real-time features capture immediate user behavior, while batch features provide historical context. What happens with cold start users or items? We'll need a fallback strategy, like popularity-based features. Data quality is paramount. We'll use monitoring and alerting to detect anomalies. We use Kafka because its append-only log gives us replay capability. If our consumer crashes, we don't lose events. Let's engineer some features. We need user features like demographics and past interactions, item features like category and price, and context features like time of day and device type. We'll also use embeddings to represent users and items in a low-dimensional space. These embeddings can be pre-computed offline and stored in the feature store for fast retrieval. The mistake most ML candidates make is treating all features equally. A senior engineer focuses on feature importance. Pause here. What features would you prioritize to minimize latency and maximize accuracy? Remember this embedding dimension. It comes back during scaling. Now let's design our model architecture. We'll start with a simple baseline, like a collaborative filtering model. Then we'll move to a two-stage approach. Candidate generation followed by ranking. Think of candidate generation like a funnel, from millions of items down to hundreds. For candidate generation, we'll use a two-tower model. This model consists of a user tower and an item tower, which independently encode users and items into embeddings. The dot product of these embeddings gives us a similarity score. For ranking, we'll use a transformer model. The interviewer might ask, why a two-tower model instead of a single deep model? The answer is latency. Two-tower lets us pre-compute embeddings offline, while a cross-network requires real-time inference for every pair. The two-tower model is like speed dating. Quick compatibility check first, deep conversation, ranking only for top matches. Let's discuss training. We need a robust training pipeline that can handle large data sets. We'll use negative sampling to address class imbalance. We'll also use offline evaluation to measure model quality and A/B testing to compare different model versions in the real world. A senior engineer would also consider shadow mode deployment to monitor model performance without impacting users. Remember those millions of dollars wasted on models that never ship? Rigorous offline and online testing prevents that. Now let's dive into serving. This is where we optimize for low latency. We'll use an embedding cache to store pre-computed user and item embeddings. The embedding cache is like having cheat sheets for common questions. Instant recall without recalculating. We also need to decide between batch and real-time inference. For most use cases, real-time inference is essential. The interviewer will probe what happens at 10x scale. The embedding cache handles 90% of requests, but cold start items need a fallback to a lightweight heuristic model. Latency is king. We'll optimize the inference pipeline to minimize latency. A senior engineer would ask, what are the P95 and P99 latency targets? We use a cache-aside pattern with Redis. On a cache miss, we query the DB and backfill the cache. This keeps our P99 under 50 millis for read-heavy workloads. We've designed a low-latency serving architecture for real-time ML inference. The key trade-off is latency versus accuracy. A simple baseline gives us low latency, but low accuracy. A two-tower model offers a good balance. A transformer model provides high accuracy, but at the cost of increased latency. If I had more time, I would explore model distillation to compress the transformer model. Remember that 90% failure rate from the beginning? You now have the tools to avoid that fate. Click here to subscribe for more ML system design deep dives.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.